Hi everybody and welcome! In this video I'm going to share the 8 papers that I liked the most at ISMIR 2021. If you're wondering what's ISMIR, well, that's probably the most important conference in AI music. And the ISMIR acronym stands for International Society for Music Information Retrieval. This year the conference was held in November from 7th to the 12th, and it was held online because of the pandemic. I particularly liked this year's iteration of the conference because of its breadth. I mean, the topics covered were a lot, and they covered all sorts of AI music fields, from generative music to core music information retrieval tasks, like, for example, music cover detection, to empirical studies in music psychology. So, I mean, I was really impressed. There were a lot of researchers, probably more than 100, and I really liked also the vibe and the discussions that just sparked out of like the poster session that we had. So yeah, that was fantastic. Now, my goal here is just to give you an initial overview, an initial introduction of these 8 papers. I'm not really going to dig too much into them because, of course, I don't have the time, because otherwise I would have needed, I don't know, 8 hours perhaps, not just half an hour or whatever like amount of time this, whatever duration like this video may end up having. So yeah, I'd say let's get started directly like with the first paper. And another thing that I want to say before digging in is that, I mean, these are not the 8 best papers. These are just like the ones that I liked the most. And I also try to take papers like from different sort of like fields or specific tasks, just like to give you an overview of the type of breadth that we had in the topics covered. Okay, without any further ado, let's start from the first one that I really loved. It's called "The Words Remain the Same, Cover Detection with Lyrics Transcription." Now here you see that I'm also having the link to the slides as well as to the paper itself, and I'm going to do this for all the different papers. And don't worry, here I have like a lot of notes that you can then like take a look at, because I'm going to share the link in the description box below so that you can have easily access to that. Okay, so what about this initial paper? Well, the sort of core idea of this paper is that of performing music cover detection. Now, you may be wondering, but what's music cover detection? So let's quickly go to the slides that were used during the presentation by the authors. And so cover detection is basically the identification of several interpretations or renditions of the same musical piece. Now, the traditional way of performing cover detection is that you want to get rid of variant musical features, so all things that are connected to tempo, key, timbre, structure, and retain the musical invariance. And in this case, we're talking about melody, usually, and chord progression and harmony. The basic idea here is that if I have different renditions of the same paper, I may be changing tempo or key, but the main melodies, the main chord progressions, hopefully, will be retained. Now, the great idea that the authors had here is to leverage lyrics information extracted directly from audio. So they basically framed the cover detection here as a noisy text matching task. So what the authors did basically was to take a very interesting hybrid approach, which was a fusion of a singing voice recognition framework, which was used to extract the lyrics directly from the tracks, and then paired that with a classic tonal-based method. And for both of like these models, so the SVR, a singing voice recognition, and the classic tonal-based cover detection, they used pre-existing models. So the sort of novelty here was to bringing these two things together. Now, the system works like this. So you have an audio pair, so X1, X2. So it could be like the original track, and then you have like the rendition, the second rendition or variation or the cover of that initial track. And then what happens is that all of these tracks, both the tracks, go through the singing voice recognition and the tonal based matching process. So the singing voice recognition is going to extract lyrics both from the original track as well as the hypothesized rendition or cover of that track. And then the system is going to do a sort of like string matching to see if the lyrics are close. And if they're close, well, perhaps we do have a match there. So the rendition could actually be a cover of the original track. And then at the same time, the tracks go through the tonal-based matching model as well. So you have like these two parallel systems for cover detection. Now, of course, there's also an instrumental detection classifier here that's used to see whether the tracks analyzed have lyrics or they're just instrumentals. And of course, if they're just instrumentals, then I mean, there's no need to have singing voice recognition because there's no lyrics to transcribe, right? And basically the idea is then with the information coming out of the string matching as well as that of the tonal-based matching, we get to a sort of hybrid score that will tell us whether or not this audio pair is somewhat linked, or in other words, whether like one track is a cover of the original track or the other track. So yeah, I think like this sort of hybrid approach is really interesting, and it's also multimodal. So it's basically leveraging more information than just the music and raw audio itself, but also relying on text information. So a couple of takeaway points here. So the authors found that using lyrics, even if noisy lyrics and transcriptions, can significantly help for cover detection. So basically, using this hybrid approach improved on the original tonal-based matching system. And the second point was that the information carried by lyrics is often complementary to the tonal-based information. And this is great news because basically like the two systems can complement each other. So yeah, really interesting idea about cover detection, which I think can also be used in other use cases. So basically go for multimodality and use hybrid systems as much as you can, because the more systems you have, the more variety of information you're going to be able to extract, the better your system will perform. Okay, so let's move on to paper number 2. So here the title is Cross-Cultural Mood Perception in Pop Songs and its Alignment with Mood Detection Algorithm. Okay, so what's this about? Well, this is basically a cross-cultural empirical study that's been performed to study how convergent or divergent people are in perceiving various emotions in music. So the sort of research question is, do people from different countries or different cultures perceive musical emotions differently? And to do that, to like respond to that question, what the authors did was carrying out a sort of empirical study with 166 participants, which came from 3 different countries, from Brazil, from South Korea, and from the United States. And so they basically provided different types of music, so Brazilian music, South Korean music, and music from the US, to these 3 groups of people from different countries. And then they asked them like to give sort of like annotations regarding 9 mood categories. And some of these mood categories were cheerful, calm, sad. And basically then they sort of carried out some sort of basic statistical analysis to understand whether the perception of moods was different across people from different cultures or different countries in this case, and whether people listening to music from different countries had like different perceptions, right, of the moods. And the takeaways were really interesting, so the results. So most moods are highly agreed cross-culturally. And so this is an interesting take because it seems like that moods can be thought of as a potential music universal in music. But then the question is whether like this sort of universality comes because of music globalization or just because music, so like the way we compose music is sort of rooted like to biological cognitive constraints that then make it accessible to other cultures as well. But regardless of this deeper understanding, what came out is that most moods are highly agreed cross-culturally. And there's a but here, more complex moods or nuanced moods, like for example, dreamy or tense, may be more cultural dependent. So there's less agreement in those cases. And finally, they also try to answer to an interesting question, which is whether state-of-the-art mood detection systems are biased towards a certain culture. And the answer, surprisingly, is no. It seems like there are no biases in a state-of-the-art mood detection systems. So yeah, this was a really interesting empirical study. Let's move on to the third paper. This is titled A Modular System for the Harmonic Analysis of Musical Scores Using a Large Vocabulary. Okay, so I really liked this paper. And basically what the authors did in this case was to build a modular system to perform harmonic structure analysis on symbolic data. Basically on symbolic music data like MIDI, right? And what they wanted to extract is all the harmonic information from the lower level up to the higher level. So what's this information? Of course, it's the key in terms of tonic and mode and the different chords in terms of like the root, the type, and the inversion. So the idea that they used was to divide the problem into multiple modules. In other words, to arrive at a complete analysis, the system carries out different tasks in a sequence. So we have different modules which take care of different parts of the harmonic structure. So we have an initial chord model that's given basically like calculates a first key given the first chord, and the system that they used to do this was quite simple because they just used a simple distribution based on counts from the training corpus that they had. Then they had other modules, so the key sequence model, which would actually guess the key given the relative chord sequence. Then the key transition model, which would guess a key change given the relative chord sequence. Depending on the chord sequence, it would guess whether or not we do have a key change, say, for example, moving from C major to G major. Then these other module, chord sequence module, basically tries to determine a relative chord given the relative chord sequence. And then we have a chord classification model, which tries to establish an absolute chord given the input notes. So now, what's the difference between a relative chord and an absolute chord? Well, the absolute chord is what we call like C major or D minor, right? Whereas a relative chord, it's sort of Roman numerals. So like the first degree of the scale, the fifth, the seventh, for example. So it's relative to the key, and it sort of it's connected to the idea of functional harmony. And finally, we had this model, not model, but module, which is also a model, by the way, that's called chord transition model. And this one sort of tries to establish whether we have a chord change given an input note or input notes. Okay, So the interesting aspect of this approach, which I like quite a lot, is that they're trying to inject into their system, first of all, modularity, and then music theory knowledge. Music is a very, very complex endeavor. It's very difficult for a flat system, even a deep learning system, to get all the nuances of music, because music is such a complex system and a hierarchical system that needs to be approached through intelligent representations and knowledge. So in this case, what the authors are doing is they are providing to the system that knowledge and that music representation and music theory that's necessary to understand the different parts of harmony at different hierarchical levels. And I think like this is extremely smart. Now, let me say one thing about like these models, and I think I may have, yeah, I said that down here. So each of the modules can be replaced easily as long as they follow the same input-output interface. So this is like the great idea here. For like the different models, they used a LSTM or sometimes a bi-LSTM deep learning model, but potentially, as long as like the different modules here have the same input-output, you can just switch one model for another model. So perhaps tomorrow you want to try out the key transition model being a transformer model. You can do that because the system is very modular. Okay, and so this is a sort of like graphical representation of how this works. So we just get the input here, and the first thing that happens, if I remember correctly, is the code classification model that starts and say like it just like identifies C major, and then this information is passed to the initial code model, which is the module responsible for identifying a key, and here a key is established, right? And then the other information is used for example, in this case, the code transition model outputs like all zeros when we don't have a transition, or a 1 when we do have a transition. Then the code classification model pipes the information into the code sequence model here, which takes like those absolute codes and it transforms them along with the information regarding key into Roman numerals or a functional harmony. In this case, C major is the first degree of the scale. In other words, it's the tonic. And finally, we have the key sequence model, which guesses whether or not we do have a key change. So in this case, we don't have like any change here, We're still in C major, but here, the key sequence model finds a key change. So basically, we are moving towards the 5th degree. In other words, in this case, towards G major. Okay. Yeah. So I think also like a couple of like goals like to talk about like regarding this system is that the model each aspect, so the basic idea is that of like modeling each aspect of music at the appropriate level using like different modules for different hierarchical levels. And then the model wants to output an output that should be understandable. And we can easily understand the reasoning of the model here because the model reflects on all the different hierarchical levels of harmony. So in other words, this is not a black box model, but we can understand what's going on inside the system. And here we have like an example of this model, which some things that the model like got and others like that. I mean, like in green, I guess, and then in red, like the ones that it didn't get. Now let's move on to another one. So does track sequence in user-generated playlists matter? So this is also like a very interesting type of study. So the authors in this case investigated the importance of track order in user-generated playlists through a data-driven approach. In other words, they took the million playlist data set, and they analyzed about 700,000 playlists, trying to extract information regarding variants of the playlists or within the playlist. Okay, so the first research question was very interesting, and it was, does the sequence of tracks matter in user-generated playlists? In other words, do users create playlists caring about order, or is the order completely useless, right? Do they don't care at all about order? Right. So how do you approach this type of problem? And I think like here it was like very insightful, like the way they did it. So authors approached this question by comparing the variance of subsequent tracks to the overall playlist variance in terms of a variety of properties concerning track metadata, like for example, artist, genre, but also audio features like acousticness, danceability, or energy. The basic intuition here is that if the playlist variance, so the variance across the whole playlist for different acoustic features or track metadata is greater than the so-called sequential variance, then order counts. So what's sequential variance? So sequential variance is variance calculated across tracks that are close to each other, right? So in other words, they're saying if the overall playlist variance, so the variability of certain acoustic features is greater across the whole playlist, then the same variance for tracks that are close to each other, then what we are saying here is that the tracks that are closer to each other are going to be more homogeneous, more similar, and therefore their variance is going to be less, and it means that order counts because those tracks, subsequent tracks, have been chosen and put together because they are closer to each other, so they are more homogeneous. So there's a rationale behind the way that the order was put together, right? It's less random, there's more intentionality there. So yeah, this is a clever way of testing out this question. So does the sequence of tracks matter in user-generated playlists? And here we have a lot of scatter plots. So on the x-axis, you have playlist variance, and on the y-axis, you have the sequence variance. And here, each dot in this scatter plot is basically the value for a single playlist, right? In the playlist variance, sequence variance 2D space here, right? And what we see is that usually playlist variance is higher than sequence variance. And we can easily see this because most of these dots are below like this line here at 45 degrees, right? Which basically means that, like the playlist variance is higher because the slope of all of these graphs tend to be like lower than 45 degrees. Okay. So this is an interesting way of seeing visually that the variance for the playlist is higher than that of the sequence. Okay, which basically means that in a sense, order counts. The second question authors ask is, for how long do properties of one track persist on its successors? And authors studied this question by evaluating the number of tracks that are affected by the previous ones concerning the aforementioned properties. And here we have a graph across all the different properties, so genre, artist, popularity, loudness, and you see that it goes down over time. Let's take a look at the results and takeaways for this study. Authors find that metadata like genre, artist, and popularity vary on average by 15% more for the overall playlist variance than for order-dependent sequential variance. In other words, in user-generated playlists, having homogeneous playlist counts to a certain extent. And the answer to the initial question, which was, does the sequence of track matters in user-generated playlists, is yes, to a certain degree. And then authors also found that the effects of the audio features, loudness, energy, danceability, acousticness, and valence persist stronger in subsequent tracks over a playlist than other properties such as metadata. In other words, we want, or users want, for their music to be acoustically coherent, more than coherent in terms of metadata, like same artist or same genre, perhaps. Cool. So this was a great empirical study. Let's move on to a deep learning study that's called Semi-supervised music tagging transformer. So this was a really interesting paper, and not that much because they are using transformer for technology, or transformer architecture for performing music tagging, but rather because of the semi-supervised approach that they used, which was really, really interesting. So let's take a look at the notes here. So current music tagging models behave like a bag of feature models. What this means is that this music taggers usually don't take that much long-term relationships into account when tagging or when detecting different types of tags. So what authors want to do is building a model that interprets music as a sequence, right? Leveraging this sort of time series based information that a music carries with itself. And of course, for that, they want to use transformers, because transformers are incredibly good at capturing long-term relationship in data. Now, what's the sort of basic problem that they want also to address? In general, there are few labeled data and abundant unlabeled data. So you have a lot of tracks, but only for a few tracks you have labels, or in this case tags. And so what authors want to do is to utilize unlabeled data together with labeled data. In other words, leverage the unlabeled data beyond the labeled data. And in order to do this, what they do is using a semi-supervised technique that's called noisy student training. And we'll take a look at that in a second. So initially, let's just take a look at the model itself. And the model is divided into two parts. So there's a front end that uses a CNN to extract features locally, and then these features are fed into a transformer that hopefully will be able to find the long-term relationships, and as an output it will just identify different tags for a certain track. Okay, so now what's the key aspect here is, as I said, I'm not super impressed. Well, I'm impressed by the results by all means, but I mean, I'm not that interested into the transformer technology as I am in the noisy student training part of this work. So they used this semi-supervised approach to leverage also unlabeled data. Let's take a look at how this works. So here you have labeled data, and here you have unlabeled data. And of course, unlabeled data is way more than labeled data. So here, for this type of training, you have two models. You have a so-called teacher model and a student model. The noisy student training goes like this, step by step. First one is to train the teacher with a simple supervised method, and you would train the teacher only with the labeled data. Then in step number 2, you train the student, but with two losses. So you have the loss for the typical supervised approach, which you would use in conjunction with label data, and a loss for the pseudo labels generated by the teacher on unlabeled data. What does this mean? Well, it means that we take all the unlabeled data, we pass them through the teacher, and of course we get some pseudo labels, and we would use these pseudo labels and pass them to the student, of course, along with the audio data, audio unlabeled data that we have here. But these are pseudo labels, so we need a loss that's specific for pseudo labels. Okay, and there's a final step here, which is that of applying data augmentation to the samples showed to the student to improve on students' performance. Here, there's a mistake. To improve on students' performance. So in other words, we take all the audio data, we augment that data, and then we pass that augmented data to the student to increase the variety also of the type of data heard by the student. Okay, and the great thing is that you can do this process iteratively, because now the student can become the teacher, right? And you can have a second student model that can be trained on the new teacher, which is student number 1. In terms of data augmentation, they used polarity inversion, additive noise, random gain, filters, so low pass, high pass filters, delay, and pitch shift. Now, another interesting thing about noisy student training is that you can also do so-called knowledge distillation or expansion, which basically means having a student that, in the case of distillation, has fewer parameters than the teacher, and basically you're trying to distill all the information that the teacher has learned and to come up with a model that's smaller in number of parameters than the teacher. And this is particularly good for when you have a situation where you need to be very efficient computation and memory wise. Say, for example, you want to deploy this model on an edge device. So yeah, there's also something interesting to keep in mind about noisy student training. Right, so let's take a look at the results. So here we have some model comparison. I can't remember actually where they tried, so the data sets that they used for this type of evaluation. But as you can see, all in all, the music tagging performer and the music tagging music tagging transformer and the music tagging transformer with data augmentation basically are state of the art. So they beat the state of the art in music tagging. So here, for example, I recognize musician, which is sort of state of the art CNN-based model for music tagging. Right. And also the interesting aspect is that the transformer, when compared to a residual network, is able to have performance that remains best or remains better, even with longer chunks of input length, right? So in this case, for example, you can see that the performance remains more or less at the same level, moving from 5 seconds all the way to 30 seconds, whereas in the case of ResNet, this tends to go down. Of course, these are not huge variations, but I mean, given the minimal advancements that you have at these levels of proficiency of these models, then yeah, it's definitely relevant. Let's take a look at some takeaways. Transformer slightly improves on CNN-based models and the claimed state-of-the-art in music tagging. Music tagging transformer reports consistent performance for longer input, and music tagging models can be improved with strong data augmentation, as we say. But for me, the most interesting part of this paper remains this one. So the performance can be further improved using noisy student training. And both knowledge expansion and knowledge distillation enhance music tagging performance. And now we get to a paper on generative music, which is definitely in line with my research interest. The paper is titled Controllable Deep Melody Generation via Hierarchical Music Structure Representation. And I think here, the very interesting aspect is that authors use this sort of hierarchical approach and inject a certain degree of music theory, which once again, it's necessary to be able to unpack a deep learning black box approach and then give interpretability to the user of this model or the potential user. But let's dig a little bit into it. So authors introduce music frameworks. So this is a hierarchical music structure representation and at the same time a multi-step generative process that we can use to create full-length melodies which are guided by long-term repetitive structure, chord, melodic contour and rhythm constraints. On a very, very high level, this is the sort of model that we are looking at and the different components. So you can input a song in MIDI. So here we're talking about symbolic music once again. The system has an initial encoder which will perform a certain analysis and will reduce the initial MIDI song into a hierarchical representation that is part of the music frameworks. And then you can manipulate this higher level representation to generate new melodies that are inspired by the initial song. And the output here is a song. And as you can see, this is a sort of pipeline that has these two parts that are so common in generative music. You have an analytical part that boils down the complexity of a piece of music to an interesting hierarchical representation, and a generative side that leverages that higher level representation to generate new music or variation of the original piece. Okay, so as I said in the first part, in number one here, music is reduced to basic melody and rhythm. So this is, for example, an original melody that we have here. What that component of the system does is extracting a basic melody. So as you can see here, this is a sort of simplified melody of the original melody that we had here. And many of this sort of embellishment notes just like get cut out. It really resembles a sort of like Schenkerian analysis for those of you who are more familiar with musicological theories. Okay, so then the other thing that this reduction does is getting to a basic rhythm form. So we start with a full melody and then we go down to a basic melody, so basic pitch plus basic rhythm form. Okay, so now that we have that music representation, hierarchical music representation, it's possible to change either the rhythm or the basic melody and then regenerate the phrase by using a transformer LSTM model here. So once again, let's take a look at this. The input song comes in, and we have information about chords here, and then we use the music framework hierarchical representation, which reduces the initial song into its basic rhythm form and the basic melody. Then we can change either the rhythm or the melody, the pitch or the rhythm content, and then we get a new melody. And the great thing about this is that you can potentially build a whole section using this idea of variation and repetition. So we start from a musical phrase, and then we get all the way to a whole section by repeating or varying the same musical phrase. And here you have an example. So in a measure, we have the basic melody, the basic rhythm form, and the chord information. Then here, if we sort of like join multiple measures, we arrive like at the phrase level, and then we can use like that sort of regeneration approach to create variations on the original phrase. So for example, you move to A to say here like A prime, and then you can just expose, put together different sections and repeat them and vary them so that you can create a larger form musical piece. And so this is, I think, once again, a really, really smart approach. And the most important takeaway here is that to generate music and to analyze music, just we saw with the harmonic detection system, you need to inject a certain level of musical understanding in your system and have the right music representation that most of the time needs to be hierarchical. Let's remain in the space of music representation, but now let's focus on audio music representation. And the next paper is titled Contrastive Learning of Musical Representations. Here, the idea is to leverage very good audio representations of musical pieces in order to perform music information retrieval tasks like music tagging or music genre classification. So the authors start with this problem, which we've seen already a number of times, and it's extremely true, especially in the industry. Labeled music datasets remain hard and time-consuming to create, and that's true because you need a lot of expertise and time to create those annotations. So what authors ask themselves is, how can we methodologically improve learning for smaller datasets? The intuition is that of learning useful representations or useful embeddings without having a ground truth. And in order to do that, authors used contrastive learning. And these embeddings that they created and the model that they created to get to these embeddings is called CLMR. To learn these embeddings, authors used a multi-step approach. First of all, they extract a section of a song and they apply data augmentation to this section stochastically, and they pass this audio data through an augmentation pipeline where you have reverb, noise, pitch shift that's randomly added. And in this case, what happens is that these will be the positive examples that the contrastive loss will see. And then the authors will also take a negative example, which will be a passage from another piece of music. And the sort of basic idea of how contrastive learning works is like this. So you have the sort of anchor, an initial token, and then you want to pass to the contrastive loss a sort of a positive example, so a token that's very similar to the original token, and then a negative example, so something that's very dissimilar to that. And the contrastive loss will be able to learn the differences and create a representation that's going to be meaningful for that data that you have. In this case, the positive example is given by the augmented track. So here's the sort of very, very insightful idea. So basically using data augmentation as a way of creating variations that are going to be positive examples for the contrastive loss, and then the negative examples will be just passages from other tracks. Okay, so now we have positive and negative examples or data points. Then we're going to go through a couple of quite technical steps. I'm not going to delve into them. You can definitely read the paper if you want more information. But basically, we're going to have an encoder that takes the augmented examples and it maps them to their latent representations, and then a projector that maps the encoded representations to the latent space where the contrastive loss is formulated. And finally, we use contrastive loss to identify the positive-negative pairs passed in the same batch. So it's not important, I don't think here the important point is necessarily the detail of it, but rather that at the end of this approach, you're going to have embeddings that are semantically relevant music representations, or like meaningful audio representations of the original data that you had. And then what the authors did was using these embeddings and passing them to a linear classifier and training a simple linear classifier using these embeddings on a bunch of different data sets like Magnatag Attune, MSD, and they basically show that they have pretty good results in music tagging and these things. So the basic idea here is that with very little labeled data, CLMR representation outperforms traditional supervised methods. In other words, this means that it's possible to obtain decent results even with a small data set given the initial CLMR representations. And the sort of corollary of all of this is that CLMR representations distill important information. So they bring very meaningful information. And here you have a graph where on the y-axis you just like have the Prouk curve for music tagging, and here you have the percentage of labeled trained data used for fine-tuning the models. So here we just use 1% of the data on a supervised model, and here 1% of the data that was data expressed in CLMR representations and then used to train a linear classifier, right? And as you can see, there's more than 10% difference between the supervised and the CLMR embeddings approach, which is massive. Okay, so some takeaways for this very interesting paper: and no pre-processing and no ground truth required to learn effective representations. And I think like this is key. So you can basically reuse audio data that's completely unlabeled to arrive at quite good music representations. Then linear classification shows strong performance despite being a challenging MIR task, right? So we see that a very simple linear classifier is able to do a very good job at complex tasks like music tagging by using the right music representations. And the cool thing is that we can also sort of like transfer this representation to other domains. So yeah, this was a really, really interesting paper, which once again pushes us in the direction of looking more into music representation and less into the model architecture themselves. Now we have the final paper, which I also really liked, and here we're talking about something that's quite different. So we're talking about music similarity measures, and in this case, for this graph, for this paper, the authors used a graph-based approach. The title of the paper is An Interpretable Music Similarity Measure Based on Path Interestingness. So the authors, it's two of them, Gabolini and Bridge. So authors developed music similarity metric using a knowledge graph. And the knowledge graph represents semantic relationships between artists, songs, and sort of different music items. And so here you can see, for example, an example, right? So you have Alice Coltrane, which is an artist type of node. And here you have the edges, which have like different meanings attached to them. So it has grandnephew is one, can be another relationship. So Alice Coltrane is a solo artist, just like Thundercat here. He's also a solo artist. Cool. So how do they calculate similarity? Well, the basic idea here is that they find paths between artists. So they find paths which connect one artist to another artist, and then they score the paths based on interestingness, right? And then they aggregate these scores to determine similarity. Now, the key here is this interestingness approach. So each path is going to get an interestingness value, and this is measured through a linear combination of the popularity, the rarity, and the shortness of path. Now, if you want the details about how all of these metrics or variables, if you want, are calculated, you can go check out the paper. It's very, very clear. But I think like it's really smart to think about like interestingness in terms of like popularity, rarity, and shortness of path, and balancing like them out. So what's the advantage of this approach? Well, the advantage is that the similarity metric is very interpretable, and it's interpretable by design because it's actually based on a knowledge graph, right? So in order to evaluate their proposed system for music similarity, the authors used a few evaluation baselines, like a random, counting just the number of edges in a path, or this other LDSD approach, graph-based approach. And they calculated the results, and in this table we can see precision at 5 on a bunch of different data sets like Myrex, Last.fm, and Facebook here. And as you can see, IPSIM, which is the name of this system, it's basically outperforming like all the rest most of the time, which basically means that the system is kind of like potentially working, which is nice. Good. And with this, we conclude this very, very long video. I hope you enjoyed this review. It wasn't really like that quick, but at the same time, I wasn't really digging into each of these papers as I could have done had I just like focused on each of them in a separate video. Once again, all of the papers are available with their slides, not just these 8, but all, I think like the 100+ papers that have been published in ISMIR 2021. So I highly suggest you to go check out the proceedings. Now, another thing that I highly suggest you to do is, if you're not already a member of the Sound of AI community, I highly suggest you to go check that out and to actually sign up on the Slack workspace. And here I leave you like the link in the description box below. And another thing, as I said, this document is going to be accessible to you, and I'll leave the link to a Google Doc, a version of this, in the description box. So I hope you enjoyed this video, even if it was quite long. Let me know if you attended ISMIR, or if you just read a few papers there, and let me know which are the papers that you liked the most. That's all for today. I hope you enjoyed this. Take care for now.